Okay, so now we will use some program to analyze or to design this experiment of the frogs and toads. So for that, we will use this design expert. So we will start using the design wizard. So what we are doing is a characterization experiment, and we will not enter into what are the other two options. And then we have factors, and none of them is hard to change, and all are categoric. So we have three factors. One is the species. And the species has two values that are frog, toad. Then we have moisture, that we have wet, wet and dry. And then we have a hormone. Is we can give treatment. We can give control, that is nothing, and hormone. Okay, so now we have everything. Now we move into the next, and into the next, what we have is we have to define the model. So we see this is the equation that we have in our slides. So in our slides, let's go to the slides. The slides is our observations is an intercept, so an overall mean, plus something that depends on the main effects, plus something that depends on the second order effects. And in this equation, I forgot to include the third order effects that were later analyzed, but we have them here, so we can include them or we may not. So let's say that we are not interested in the third order effects, so we don't include them, and then what we do. So let's do it as we did in the slide. So now we have the three full interactions. So you see we have modified. So modified, this is, if I remove one of them, this is modified because it doesn't fit into any one of them. So I have either modified or main effects that are just these three, or second order effects or third order effects. Okay, so we have the three order effects, and then we have the lack of points. So this is the number of, so how many parameters do we need? How many degrees of freedom do we need? So we have 3 here, we have other 3, 6, and 1, 7. So we need 7 degrees of freedom for the estimation of the parameters of the main effects and interactions. And then here it is proposing to use 13 runs, so 13 animals in total. And because we are using 13 minus 1 is 12, and because we are using 7 degrees of freedom for the parameters, there are 5 degrees of freedom for the residuals. So 5 is too little. So let's see if we can put 15, for instance. Then we will need 23 animals. And let us add one more so that we have 24 animals. So we have 24 animals, and then we can go for the next step. And here we have also what we are doing is optimizing. These are criteria. The optimality produces a design that best estimates the effects of the factors, which is particularly suited for screening studies. The algorithm picks the point that minimizes the volume of the confidence ellipsoid of the coefficient. That is, minimizes the determinant of X transpose X inverse matrix. So you see that the system matrix that we were introduced at the point of least squares is really the important so when we design the experiment, what we are doing is fixing some properties of X transpose X. And here, it is minimizing the trace of that matrix, and each one has its own theoretical justification. So let's use this one. And then what are we measuring? We are measuring the weight D, and we want to detect things that are twice the level of noise. So assuming that the standard deviation of the noise, the important thing is the ratio. So assuming that the standard deviation is 1, then we want to detect changes that are twice that 1. So the ratio is 2. And then we see that with 16 animals, or 16 degrees of freedom for all the, so 3 animals per combination, what we have is a lot of power. So maybe we don't want to have such a high power, and we can reduce the number of animals. And this is because we want to detect changes that are twice above the level of noise. So we can do 2 things. So first, let's see if when we change the sensitivity, so now, so we have a power with 16 animals, or 60 extra degrees of freedom for the errors. We have a sensitivity of 60, over a power of 64% to detect changes that are only one time above the level of noise. So they have the same amount of signal and noise. And we saw that we had 99.6 for changes twice the level of noise, and probably for a more decent power, for a more normal power, we have something like 1.5, a little bit less, or 1.4 probably. So 1.4, then we have 90. So we can do multiple things here. So we can keep this sample size because we are happy with the power that we have, or if our aim is to detect things that are twice the level of noise, then we fix here this to 2. So we fix this to 2, and then we reduce the sample size. So we don't need so many animals then. So we can use a few less. So still we have a lot of power. So let us reduce it even more. So let's say 8. We have 95% power. So let's say that let's try to aim at 90. So yeah, now we have 90 in the 3 factors. And now we can finish. And we see that we don't need 16 animals to do this experiment. We need only 14 animals to do it. So this is a reduction in the number of animals. And then you see that the runs are randomized. So we don't do all frogs first and then all toads, and the same for any of the other conditions. Instead, we can sort them so that we can have a better picture of what we are doing. So you see that we are doing only 1 frog wet control. We are doing 2 frogs wet or mold, 2 frogs dry control. So the design is not balanced, and it cannot be, because we have 8 groups and we have only 14 animals. So some of the groups necessarily cannot have 2 animals because we have fewer than 16. And still the runs are aleatorized or randomized, so we can sort by the run. So the idea is that you can design your groups, and once you have your groups, you randomize them, and this randomization will remove possible biases induced by time, or the person doing the experiment, if it is changing along the experiment, or whichever other factor that may change over the course of the course of the experiment. And so this would be all for this example. Let us now go for a second example. So we don't want to change this. And let us go now for the example of the tomatoes. So let us look for here. It is pass, it is design expert. We have design expert, and we go for the design wizard, and then we don't have anyone that is hard to change, and then all are categoric. We have three treatments, three factors. One is rows, and we have three levels here. So we have row 1, row 2, 3. Then we have columns. We also have three columns, and we have column 1, column 2, column 3, and then we have treatments. And treatment, we have three also, that is control, and then treatment A, treatment B. Okay, so then we change the model, so we don't want the interactions because the first two are really blocks, so we don't want to compute the interaction between blocks among themselves or blocks and treatments. And then we can leave it as it is. And so let's see how many. So what we are measuring is the weight of the tomatoes. And again, let's say that we want to detect changes that are twice the level of noise. So we see that we have very little power. So we will increase the number of lack of fit points. So now let's say 10. Let's try to make it an even number. So still we don't have enough power. We increase this even further. So let's say 17. Now we have enough power for two of them, but not for the third one. Okay, so let's increase it a bit more, 19. And then I hope that we have enough power for the three factors. Okay, so now, again, these are all the runs, and let us sort them. So here time doesn't have any meaning because we will do all these experiments at the same time. And then what we see is that we have to split each one of the subplots. So row 1 and column 1 has three treatments. So we will split it in three parts. In one of the parts, we will apply A, in the other part, A, and then B. So you see that they don't even need to be well balanced within each one of the groups. So then we would have row 1, 2, we have control B, so that means that again we split it in three parts, and then we apply these ones, and then row 1, column 3, we have control A and B. So we would split, so the row and columns are accounting for possible gradients of the fertility of the soil, and then we split those regions into smaller parts, and then within each one of the parts we apply different treatment. So with this, this would be a second example in which we haven't estimated the interactions between factors because the two of the factors were blocks. Actually, that is the difference between a block and a factor. It is only a semantic difference that with blocks, you don't want to compute interactions between blocks and anything else. And otherwise, we have also seen how to increase the sample size so that we have enough power to detect whatever changes that we want to detect. So it doesn't mean that they will happen. It means that if they happen, we will have enough power to detect them. And this would be all. So with this, we finish this video. So let us stop recording.